So, Steve,
Yeah.
prior to the Ocean Data Alliance, Steve was IBM's chief data strategist and a member of the IBM Academy of Technology leadership team. He helped invent Internet insurance and the data governance industry. He served on the U.S. Commerce Department Data Advisory Council, New York Civil Liberties Board of Directors, and was co-chair of industry standards committees at W3C and OASIS. He holds 4 patents, 2 U.S. President's Volunteer Leadership Awards, has co-authored marine science papers, white papers on smart cities, and gave a TEDx talk on Africa open data. And I'm pleased to say that I met Steve and have known Steve since we did a presentation together at the United Nations. So Steve, I'm going to hand it to you, and I'm going to see if I can, if somebody can get us help getting your slides in place.
Right, this presentation is about the ocean. It's a really good follow-up from the last presentation from Anil about the environmental census, because he covered geospatial information about land. And what I hope to cover with you today is a little bit what he alluded to about the challenges we're facing gathering data in the ocean. So the first off is I want to underline the sense of urgency that we're in right now in our planet. We're in a crisis, but unfortunately, we're really not acting like we are. We're really behaving as if we have lots of time to fix things. And the reality is a lot of things are already broken. We just can't see it because they're underneath the waves of the ocean or they're in the atmosphere. We see that there are storms. We see that there's some consequences for climate change, but most of those consequences are not being borne by us directly. They're being borne by us indirectly. A lot of them are unfortunately happening to other species on the planet. We're facing a mass extinction above ground and below the ocean. And if we're not really getting very serious about how we address the issues of global warming and greenhouse gas emissions in the next year, I've heard so many people talk about how we have time to reach net zero by 2050, but we're already at 412 parts per million of CO2 in the atmosphere. And the world has never been, we haven't had this much CO2 in the atmosphere going back 4 to 8 million years. The period that we're in now is called an interglacial, this sort of brief moment in geological history in which there isn't 3 miles of ice covering the northern hemisphere, because for 120,000 years at a time, that's what happens. In the interim, for a brief period of 10 to 15,000 years, which we're sort of at the tail end of, there isn't ice at the northern hemisphere. And during that period of time, global emissions of CO2 never pierced 280 to 300 parts per million. And we're at 415 today. And if we continue with our plans to hit net zero by 2050, we'll be at 450 or 460 by then, with no plans of taking the CO2 out of the atmosphere and storing it in long-term storage. That's why I always start every presentation talking about the crisis that we're in and how we're not acting that way. So you probably have heard a lot of stories about how we can plant trees and grow forests to store carbon, but those forms of carbon storage are not permanent. Trees and soils can change rapidly. Trees burn, forests disappear, can be logged. And so carbon storage in terrestrial sources can only last about 50 to 100 years at best. The only permanent storage of carbon we have is in the ocean. The ocean is the world's largest storage of heat and of carbon. Before the industrial era, the ocean was a net emitter of carbon because there's an equilibrium that occurs between the atmosphere and the ocean. And that equilibrium changes when there's more carbon in the atmosphere and less in the ocean, or more carbon in the ocean and less in the atmosphere. So there's a relationship between the two. And it's a chemical relationship. When the ocean absorbs CO2, it turns into carbonic acid, and that acid changes the pH of the ocean, and that has an impact on ocean biodiversity. And one indicator of that are small microorganisms called plankton and phytoplankton, which live at the bottom of the ocean and swim to the top every day in the world's largest mass migration. And we can see in the last 60 years that phytoplankton populations are down 30 to 40%. And that's a massive indicator of biodiversity change in the ocean. and the carbon cycle. Next slide. Recently, I guess I have to tell you a story. Back in 2013, President Obama asked the US National Academy of Science to evaluate some experimental solutions for stimulating carbon sequestration in the ocean. And the National Academy looked at solutions like cloud seeding, where you basically try to seed the clouds with different types of chemicals to increase cloud cover. What that does is it shines more radiation out, and so the sunlight doesn't reach the Earth. It actually bounces off the clouds and that reduces heating. They looked at seeding the ocean with iron particles to stimulate phytoplankton growth. They looked at a few other technologies, and at the time, they said there were too many unintended consequences, and it wasn't possible to recommend any what might be called climate geoengineering solutions. The National Academy has an interesting white paper on that, which you can read from 2013. They revisited those assumptions at request of the Biden administration in the last year, and in December, they said, we've learned a lot since then, and we now see 6 primary ways that we could stimulate carbon sequestration in the ocean. We can do ocean nutrient fertilization, artificial upwelling, which is where you take tubes. There's nutrients at the bottom of the ocean, you bring them to the top, and it creates a biodiversity bloom. And the biodiversity absorbs the CO2, and when they die, the CO2 sinks to the bottom of the ocean. We can increase seaweed cultivation because seaweed has the same effect of drawing carbon out of the atmosphere, and then when they die, it stores it at the bottom of the ocean. We can work on ecosystem recovery. We can enhance ocean alkalinity, which is a process in which happens when the carbonic acid in the ocean comes in contact with limestone cliffs. It changes the alkalinity of the water, and a higher pH value of the water means that the ocean absorbs more CO2. And so some people have talked about how to speed that up beyond just the natural 100,000-year weathering process. And then finally, there's some electrochemical processes that they've looked at. So finally, people are beginning to look at what are some of the advanced solutions we could do to stimulate the ocean to take up more carbon dioxide out of the atmosphere and reduce global warming. But all of these run into a significant challenge, which is that we don't really have enough data. And this is what the past speaker just alluded to. We don't really have enough data about the ocean to evaluate how any of these would work and how well they're working and what unintended consequences could occur. And part of that is because the ocean is underobserved. To put into perspective, there are about 35 billion IoT sensors looking at us on land today, studying everything in smart cities, in highways, in parks, in streams. But in the ocean, there's probably less than 30,000 IoT sensors measuring things about the ocean. And the ocean is 72% of our planet. We have really just thought of the ocean for the last millennia as a natural resource that we can exploit without really ever considering how our exploitation was affecting the ocean itself. And so we don't consistently measure it. In fact, the way that marine science functions today in terms of getting data about the ocean isn't that different from the first marine science expeditions that were launched at the end of the 19th century. We send people on boats, they go out onto the ocean episodically, they stick some things into the water, they gather some samples, they go back to the lab and they study it. There's very little continuity about, has anybody been to the same spot before? Are we measuring stuff consistently? Are there any standards for how we measure it? Are we sharing the data with other organizations who might be in the same spot? And there's very little in situ continuous data collection. And these are significant challenges in understanding what's going on in the ocean. Now, this is a slide that I've talked about for many years about the value of data. Data is only valuable when it's used. It's not valuable if people can't find it, if people can't access it, if it isn't easily accessible. In fact, that data is a sunk cost. You pay for it to store it, and nobody can access it, and it has very little value. Ocean data cannot generate any value if it's just collected for scientific purposes and only used by the scientific institution that collected it. We have a lot of work to do to persuade scientific institutions to collect data and publish it in open repositories so that everybody can use it, because business, civil society, and other governments all have to use this data. And we have to find new ways of getting businesses. The private sector has an incredibly important role to play in collecting ocean data. And we have to find new models. That's what this presentation is about, to generate a revolution in the way we collect ocean data. So, well, I said this before, I guess I was a little bit ahead of my presentation. Again, there are 35 billion IoT sensors on land and fewer than 30,000 in the ocean. A lot of people talk about the Argos floats, which are this amazing program sponsored by NOAA in the United States of sending autonomous, you could call them robots, bobbing robots that measure the water column and float around in the ocean. And there are about 4,500 of them today. Maybe that's up to 6,000 today. 6,000 for 72% of the planet. It's measuring, if you put them all together, those are basically measuring an area maybe the size of Nova Scotia in terms of landmass of the ocean. And that is obviously insufficient. We would need millions, if not billions, of sensors in the ocean to understand what's happening the ocean is constantly moving, it's dynamic, it's biology, it's chemistry, it's physics, it's topology, and we know almost nothing about it. And yet it's responsible for capturing 90% of the heat on our planet and for helping protect us from the worsts of climate change, and we still don't know anything about it. So I believe we need a new IoT revolution and a global network of startups who can start finding ways of monetizing the collection of ocean data. It's not going to be easy, but we need it now because we're really running out of time. 90% of historical fish stocks, the way we measure historical fish stocks is by the amount of fish that fishermen catch, because we don't have any other we don't have any independent audits of how many fish are in the ocean. So all the information we have about fish in the ocean come from what fishermen tell us. And what they tell us is that 90% of the fish that were in the ocean 100 years ago are gone. Some species are down to 3% of the historical fish stocks that we had 100 years ago. At the current rate of exploitation of the ocean, we will probably be the last generation that can eat wild-caught fish from the ocean. That's how serious the situation is today. And again, because we can't measure this information independently, we're entirely dependent upon the world's fishing fleets to tell us how much fish we have. So I want to see a complete transformation of ocean data collection by 2025. And this is going to require large amounts of investment. And I think the only way we're going to get that type of investment is if we start to measure how much carbon is actually in the ocean, how much carbon we're sequestering, and how much more carbon we could sequester. Because it's the best hope we have for humanity and for the health of our planet to save us from the damage we've already done in the last 150 years of the Industrial Revolution and prevent the worst ravages of climate change in the future. That's what I prepared today. I apologize for being late. I would be delighted to take your questions. I realize looking at my black box, you can't even see me. My camera's been off this whole time. Now, as I take questions, I'm going to turn my camera on. Arthur, do we have time for questions?
We absolutely do, Steve. There are no questions in the queue, but I will use chair privilege and throw a question at you to get people started. You mentioned about the 4,000 odd IoT devices that are bobbing around in the ocean. There's rather more than that in count of boats. What if there was an international mandate that this little IoT sensor had to be attached to the hull of every boat out there? Is that something we could do?
Well, there are so yeah, that's a good idea. Some scientific institutions have relationships with merchant marine fleets that carry some sensors on board, and they collect some data from that. There isn't really a global data sharing network. As you may know, merchant ships run on very thin margins, and there just hasn't been a funding opportunity from national governments to put sensors on boats for that purpose. So that is something that could be done, but it won't replace the need, because boats are traveling and they're traveling in shipping lanes over the same area. So you would get coverage over certain areas, but there would be large parts of the oceans which would be omitted. And also you would always run into challenges, about change of ownership of companies, and, organizing that could take a while. That could be one alternative. Probably what we need right now is an all hands on deck kind of approach, and looking at partnerships that would probably have been unthinkable for science in the past, like working with oil companies that have platforms that could also be collecting data, or working with oil companies that are sending ships and robots into the ocean to survey oil wells to collect data. Basically working with everyone. We're going to need, I mean, the ocean is massive. It's, you can see the piece of it from your shore, but it's so massive. And so to even collect information on a comprehensive basis about small parts of the ocean, like the Baltic Sea or the Black Sea or the Mediterranean, is still a monumental effort. And so we're going to very much need a lot more money.
Right. So another possibility, how much of this information, how much of this knowledge can we pick up from satellites with, let's say, hyperspectral capabilities? Is that something we should be looking at as well?
Yes, some of it is available that way currently. You can read about, depending on the clarity of the water, the satellites that are currently up can gather some important data types, especially with spectrum. And you can infer certain things about the data that's being collected to understand certain aspects of the ocean, for sure. But you can't get very deep into the water column with at least currently with a satellite. So you can resurface things like wave height and temperature and a variety of different aspects. And from wave height and temperature and other variants, you can infer different things like the health of the Gulf Stream and a whole variety of other areas, and gravitational waves. And there's all kinds of things you can do with other data types to measure certain aspects of the ocean and compare to other things historically. That's very valuable. But in terms of measuring things like how much carbon is being sequestered by the ocean, or what the health of phytoplankton is, or the health of whale populations, or the linkages between biodiversity mass and the chemistry of the water, those things we need more ocean sensors and more consistent in situ continuous data collection. And I think it's fair to say that most of the data we collect about the ocean is relevant up to, related to how the ocean affects us. Is it safe to swim today? Is the water polluted? Are the waves too high? Is it too cold? Can you surf? We collect almost nothing about how we affect the ocean, about how are agricultural farms polluting the water with nitrates and phosphates? When is an algae bloom likely to take place? Where are the hypoxic dead zones? Because large areas of coastal areas around mass populations are often dead because there's no oxygen for fish to breathe. These aspects about the impact of us as the planet's most advanced species, our impact is almost unmeasured until just the last decade or so.
Yeah, I think the thing that resonates big time with me, Steve, is the notion that we're only paying attention to a very small portion of the ocean. To me, that if you have a call to action that's beyond the measurement process, it's what can we do with location intelligence to cover in the spaces that we're missing altogether.
I really
go ahead, Steve.
I think there's a huge role for the private sector to get involved. I think there are huge business opportunities. I think the blue economy presents enormous opportunities for startups and for large corporations to have a super positive impact on the biodiversity and health of the ocean that can also have a big impact for revenue and the bottom line. And I believe that, and then we're going to see, well, I would like to help generate, to get the private sector involved in instrumenting the ocean, because the scale that's needed is something that only the private sector is good at.
So I'd put out the invitations on your behalf, Steve, that if folks in the audience here want to get involved, I'm sure you wouldn't mind if they reached out to you.
To be delighted.
And I've got one more question. Oh, Jessica's put a question in here. Let me we can't miss out. Jessica's invoking convener privilege. Hi, Stephen. Thank you for your call to action during your presentation. Can you talk about the coral reefs and how essential they are to the ocean, and how the massive bleaching happening is putting us at risk of non-reversal? And I know that story so well from the Great Barrier Reef, because I was involved in building a digital twin of the Great Barrier Reef. Over to you, Steve.
Yeah, the coral reefs are a symptom of the larger ocean challenge of warming, because a lot of coral can exist in a very thin temperature range, and that range is being exceeded. So there's a large amount of coral reef bleaching because the ocean has become too warm, and also because the ocean's become too acidic. And then I understand there's also a relationship between the suntan oil that many of us use when we swim in the ocean and its toxicity to certain types of coral. And we can probably look at the coral reefs as a leading indicator of ocean health that's visible to us because it's close to shore. And in our lifetimes, we can all remember when coral was much healthier. So just in our lifetimes, we can look at that and see how much it's changed. And you're only viewing, as Arthur, as you said, you're only viewing a small fraction of the ocean when you look at the coral reef. It just happens to be the part that it's visible, it's beautiful, and it's not, or it was beautiful, and now it's gray, and it used to be colorful and full of fish. And so that's just the opportunity for ordinary people to experience the biodiversity loss that's occurring across the ocean on a much larger scale. So think about coral reefs as a biodiversity indicator on the ocean's health.
Thanks for that, Steve. Milad, and I apologize, Milad, if I've said your name wrong, has a question as well. You mentioned that we need way more sensors in the ocean, but installing and maintaining these sensors are way more challenging than land sensors. And I remember you mentioning that, Steve. Do you think it can be operated ultimately? What's your anticipation?
Yes, I think so. Yeah, there are challenges with putting sensors in the water for sure. But I also know that years ago, the only weather stations that were deployed by national governments, like air quality monitors. I did an air quality pilot project in Medellin, Colombia. The government was using fairly expensive, weather stations that cost $25,000, $30,000 to measure air quality, along with other things. And we partnered with an innovative startup based in Salt Lake City, Utah, called Purple Air, that made an air quality sensor the size of a cup of coffee. And it had a Wi-Fi antenna and a Raspberry Pi computer and a couple of lasers, which measure the particles that go through the air. And you plugged it into the wall, and it cost $150. And okay, it's not in the ocean, but to me, it's indicative of, and it didn't cover, it wasn't as scientifically accurate as the government was, but when you have a sensor that a private company can make for $150 and still make money, you can deploy thousands of them for the cost that the government puts out, and you can have much more accurate data about what is the air quality where I am now. And that's the economy of scale that the private sector can bring when applied to the ocean. Because today the sensors, marine science missions cost millions of dollars to organize. And I think that private companies could come up with sensors to collect the data instead of sending people on boats. And so instead of spending millions of dollars to send a few people on a boat in harsh conditions in the middle of the ocean, we could drop sensors in the water that could sit there for years. And some of them might require, we might have to think about biodegradable sensors that when they fail, they don't clog the ocean full of plastic. There are all these types of issues we'd have to think about when we deploy them. But I know the private sector can deploy more of them cheaper and make money off of the data.
And I guess we could also add that sensors, no matter where they are, have challenges. I have a friend who measures carbon sequestration with instrumentation that's attached to trees, and his biggest problem is that the monkeys eat his sensors. They like the chewy bits around where the cables are.
Sure.
Okay, Steve. Well, I think we're out of questions here, and I want to thank you profusely for being patient with the platform issues here, and thanks so much for your presentation. I hope you'll be able to stay on for the final presentation if you have time. That'd be great. And I think I'm supposed to actually end the session as opposed to pausing it like I did before. And I'll invite the audience to rejoin us in, let's say 7 minutes or so to get ourselves started with Vic Pant and go into that presentation. Thank you, everybody.
Thank you.